All right. We left off with polar coordinates, I believe, and then you guys had to change from rectangular to polar forms. We're gonna do a warm-up in the middle of class, not at the beginning. Okay, so it'll be a warm-up for the section afterwards. So let's take a look real quick. I'll go slow to kind of ease you back into the week. So I'm calling it curves in polar coordinates. Since that's what we left off. Remember last class I said we're gonna focus more on the algebra. This one is gonna be more on the graphic, okay? And it's gonna be a lot of like plugging in points and plotting them. Now you know how to plot them. So you've learned how to express a function in rectangular coordinates how have we been writing functions in rectangular coordinates? What do we usually write?
X-axis minus.
Not points, not the points. As functions. There's an f of x, and we're always saying it's equal to. What is when you plug in an x coordinate, what coordinate does it equal? It equals a y coordinate, right? That's how we've been writing. Right. So what does that mean? That means plug in a particular value for x and plug it into the function, and it'll spit out a particular value for the y coordinate. Okay. Where x is the input and y is the output. Just reminding you of that. So that's what you've learned. So this is what we're going to do today. So in polar coordinates, we just looked at coordinates and equations, but we didn't look at functions. We write functions as r is going to be a function of your angle theta. Okay? Your theta is like your x, and your r is like your y, in terms of input out. Okay, where theta is the input and r is the output. Okay. This guy's going to be the input, and this one here will be the output. That's what gets spit out. So on the homework that you guys did this weekend, when you guys were turning a rectangular equation into a polar equation, WebAssign usually isolated the r instead of the theta, and that's because it was training you and preparing you to writing it r equaling some function in terms of theta. Okay, like r equals tangent theta, or r equals whatever, sine squared theta. Graphing it can be a little funky because, as you saw, graphing polar coordinates is new, and you kind of have to get used to it. So we're going to do an example here. I'm going to go really slow. Ask me plenty of questions, because that whole direction of theta with the angle and r can be a little confusing. So here we're going to focus on graphing. So let's graph. Oops. I forgot one last thing here. We call the graphs of these functions polar curves. Polar curves. So the homework will say that. It'll say graph the polar curve of, And this time we're gonna do R equals cosine theta. But- Because we're doing this from the beginning, right? What did you guys, when you guys were first learning to graph things, what did you use to graph like points and stuff? What was the little thing you guys made? You made a little table, right? Like you plug in X values and you got, so we're gonna do the same thing. But just remember, what's the input in this case? Theta. So theta comes first. And then the output is gonna be R. Okay? I might need your help with a calculator. Okay. Because we want to get the whole picture, we're usually trying to use the special angles for from 0 to 2 pi. Okay. Let's see what happens. So this one's going to take a long time just because we have a lot of angles. Okay. So if you guys picture the unit circle, you have 0, right? What's the next special angle after 0? 5/6. 5/6. And then we got 5/6, and then it's 5/4, and then 5/3, 5/2, right? And then right after that is the next pi/3 one, which is 2 pi/3. And then the next 45 or the next pi/4 multiple, which is we got 45 pi/2 and then 3 pi/4. And you're gonna get 5 pi/6 and then pi. Let's just do those for now. Let's see what happens. Let's just get those points and then let's just see what we get. Okay, so I'm gonna plug in 0 into cosine of into theta. So what's cosine of 0? 1. Cosine of 0 is just 1, right? And I got cosine of 5/6. √3/2. But let's write it as a decimal because we're gonna have to plot this stuff later. Here's where I need your help. Or maybe I think I did it already. Is it 0? Is it 0.9-ish? Yeah. Okay, let's just bounce to the first decimal. 0.9. Then we got cosine of pi/4, which is √2/2. As a decimal, I believe that's about 0.7. And then you got cosine of pi/3, which is 1/2, so that's going to be 0.5. And then cosine of 90 degrees of pi/2 is 0. Okay. All right, and then you got 2 pi/3. So here, let me just stop real quick. You want to use as much as you can your knowledge of the unit circle with a little bit of symmetry. Cosine of pi/3 is 0.5. So what do you think cosine of 2 pi/3 should be? It's going to be negative 0.5. Okay, so this is negative 0.5. Cosine of pi/4 is 0.7. So 3 pi/4 going to be negative 0.7. And then negative 0.9. And then negative 1. Okay. Questions on the plotting? Or of getting the values? We haven't plotted yet. Okay, let's see how we're going to graph it. Here's where it gets going to get tricky. Okay, so I'm going to do the X and Y coordinate, the axes, sorry. And then remember, when I graph polar coordinates, I need to look at the thetas and the R's, which we were doing like little concentric circles to help us out. So let's say 1 is right here. I'm going to make it big, since it looks like the biggest value so far is in the 1s. So I have this bigger circle of radius 1. Like that. Let's say here's 0.5. So then I have this smaller circle. Okay. So if I want to plot the point 0, 1, remember, it's not rectangular points. That means for the angle 0, how long is my radius? Here, you guys are drawing. Keep finish drawing. Circles. And then I'm also going to just label the special angles. Okay, so pi over 6, let's say it's about right here. Pi over 4 is halfway. Pi over 3 is about right here. And then let's just do the same thing to the other side. It's 2 pi over 3. Here's 3 pi over 4. And then here's 5 pi over 6. And then I'm going to provide you guys with circles already made though. Okay, because this takes too long. I just want to do this one example by hand. Okay. So at angle 0, how long is the radius? Or how long is our stretch from the origin? 1. So angle 0, I stretch 1 unit. So that point should be right here. Then I rotate the radius here to pi over 6. How long is it? 0.9. See how this is supposed to be length 1? So 0.9 is just a little bit below, right? Yeah, so it's going to be right there. Somewhere around here. Then I go to pi over 4. Here's pi over 4. Here's 1. Here's 0.5. So 0.7 would be like somewhere, yeah, somewhere here, let's say. That's about 0.7. Is that okay? Yeah. How that's working? Don't think of these as X and Y, okay? Don't think of those as X and Y. That's not what we're doing. You rotate pi over 4, and then you try to stretch it around 0.7, knowing the fact that this length is 1 and this length is 0.5. Okay? It's going to get weirder. So pi over 3 is at 0.5. So I know it's exactly going to stretch 0.5 units, which is exactly right there. And then this one's weird. At pi over 2, how far do I go out? 0. So where is that? It's going to be right at the origin. What shape? And then you're going to connect the points, tracking theta as it's changing. So this point would connect to which other point? That, right, the next angle, right? Exactly. So that's how you know how to connect them. You go off of theta. So it looks like I have, what shape does it seem to make?
A circle?
Like a semicircle-ish. So that's weird. Okay, now let's get to the negatives. That's going to be weirder. So at 2 pi over 3, that's right here. But R is negative 0.5. What did we say that we do with that? You walk backwards, right? You go in the opposite direction. So if this is about, let's say that right here, that's going to happen for all these 3. So here is 2 pi over 3, but instead of stretching positive 0.5, it goes backwards here. So it's going to be right there. Okay? It's so different from X and Y rectangular graph. It's very different. So I rotate it to 2 pi over 3. Let me label these for you guys. Hold on. Just to help you if you're more of a visual person. Okay, so watch. You rotate it to 2 pi over 3 and you need to stretch 0.5, but because it's negative, instead of going towards 2 pi over 3, you go backwards 0.5 units. Then at 3 pi over 4, you do the same thing. And we saw that 0.7 right? 0.7 was about like halfway between 0.5 and 1. So here I'm going to stretch backwards that same type of distance. It's going to be around right there. Is that your hand here? No? Cool. Can look at your eyes. I can't do this on Zoom. Can't look at people's eyes. That's like the one thing I missed. Okay. 5 pi over 6. I go to 5 pi over 6, but instead of stretching positive 0.9, I need to go backwards from the origin and stretch 0.9 units going backwards. So that's about right here. And then at pi, I rotate towards pi, but instead of going 1 unit this direction, I have to go backwards, and boom, I end up back where I started. I'm right here. So if you connected the points in the order of theta of the angle, what shape do you see? It's a beautiful circle. Of radius.
If it has a positive angle and then negative arms, it'll be on the fourth point always or no?
Not always, not always, not always. No. This is because these 3 angles landed on the second quadrant. So when I go backwards, it landed on the fourth. But if I'm using a different angle, that is in some other quadrant, when I go backwards, it might land me in a different. Yeah. Is that right? Okay, so let's see. Let's just confirm it. Here. All right, so here's the circle that we have. And then I plotted the points, ignore the table. Finding the points were a little more complicated than what we did. Desmos doesn't let you graph tables with R's and thetas. That's why. Okay, but yes, look, these are the 5 points that we found. When theta was 0, what was what was the biggest value of R? 1, right? That's because cosine of 0 is 1. What do you think will happen if you put a bigger number in front of cosine? Let's see. 2. What's the diameter of the circle? 2. Whoa, chill. 2 units, correct. So if I just click a random value for A, the bigger A is, the bigger the circle. But that circle is attached to the origin. It won't move. Okay. What do you think will happen if I change this to sine? At what angle is cosine the biggest? Positive side. At zeros, at all the zeros, right? Like at all those type of angles, at 0. So where's sine the biggest? Pi over 2. So let's see what happens. Yeah, let's see what happens. So now the circle goes on top, because at pi over 2, that's where sine's the biggest. Cool. Okay. So all I'm going to need you guys to do, though, is just kind of knowing how to plot points. It's pretty much. So plot, knowing the direction that you need to connect the points. Like when you plot, it's not just plotting the point, knowing how to connect them. That's the other part that can be challenging. And this whole negative business can be challenging. Okay. So what I have is I have 2 polar functions, and you're going to graph their corresponding polar curves. I already did all this for you. Okay, but the values that you see here are just the way we did this, but with the different functions. All I want you guys to do is plot them and try to predict what the polar curve is going to look like. It could be a little challenging. Let's see. So 1, 2, 3, 4, like this. Yeah, because like I said, weather sign, or sorry, Decimal isn't too friendly with, plotting it the way we did it, yeah? I didn't give you enough. I didn't give you 4, don't give you 4. There we go. Grab and pass it back. You need one more? Okay. Then we have another. I know, right? They're so hard to peel. Here we go. Thank you. Extra? Who needs extra here? Who needs more? All right, so. The plot with points. We try to see if you can figure out what the curve will look like, polar curve. The input values, I already did that, all that work for you. If you have questions, I'll go around, help you out. They get funky, okay? If you have some kind of straight edge, like a ruler or something, that will help. The angle between pi over 6 and pi over 3, that one's pi over 4. I don't think that one's labeled. But the angle between pi over 6 and pi over 3 should be the pi over 4s. That's good. That one, you want, that was not that. No, not done to that one. Are you connecting with it? Yeah. I guess, is this supposed to be part of the graph, these connectors? Yeah, it's the first and the second. Gotcha, okay, now you're good, okay, just be careful during, it's because it's kind of like, you see how here, you didn't draw this, you just drew the point. I thought this, you were saying was part of the graph. I got it, okay. I see, so. Hey guys, can I just have you do a quick check-in with your classmates? See if you're on the right path, see if you guys' points kind of match.
No, don't worry.
When you're done plotting all the points, connect them. Don't just leave the points. Connect them with the curve.
Yes. Negative.
Because, for example, 756. You're.
I couldn't tell the difference between.
So you rotate the 756, right?
Yeah.
So the fact that it's positive, you stretch it towards that. Versus negative.
Didn't know there's much on that as well.
Are these girls? If you finish a little early, see what this graph would look like. We do that one in the back. First one, yep. This should be called a cardioid. Oh, good. So we discussed, well, these are not, like, we learned about points last class. So now we're gonna talk about graphing functions. And the graphs are called polar curves. So, in this case, instead of plugging in X to get a Y, we're plugging in theta to get an R. And the values that you get on this table are not X, Y values. They're points, coordinate, polar points. Like you did last class.
Okay.
What you get? Well, you would need to convert anything that isn't like. You need to convert things to decimals. I need a calculator for this one, okay? For the bonus. Yes. All right, let's see. Check your guys' graphs number 2. Okay, looking good. Should be negative. Guys, I made a typo for number 2. At 11 pi over 6, it should say negative 1.732. I'm guessing you guys assumed that, right? Okay, good. Sorry about that. At 11 pi over 2, 11 pi over 6, that should say negative 1.732. Isn't that? Bring this to here. Okay, let's see. We're gonna check number 1. Number 1 is 1 minus cosine theta. There it is. Hopefully you got a shape that looks like that. Cardioid. Let's see what happens if I change it to sine. It's going to be inverted. Okay. What if I put plus instead? It goes on top. Okay. All right. The second one that you guys are working on, or what is it? It's 2 sine 2 theta. Is a four leaf loop or a for loop. Okay. Let's see if I change that 2 inside sine with a 3. Beautiful. Let's change it to a 4. What do you think? How many loops? Oh. What if I change it to a 5? Ah. 6? 7? So what do you notice? Multiplied by 2, that's right. So if I put 100, beautiful, look at that. And then what do you think this 2, would, oh my God. What do you think this 2 in front of this will do? Let's change it to a 10. Let's leave it not too gnarly. So 3, 4, that's right. It just stretches the, so we won't go over this, but there's also transformations for polar functions, as you're noticing, okay? All right, guys, so, but that's, for this concept, that's all I really want to make sure you guys understand is how do you plot polar curves given the polar functions, okay? You might see this in calc if you end up going to calculus. You might see some of this show up. You will definitely see it show up in calc 2. If you're going there, okay? Now let me go back to the first one. 1 minus cosine theta. So you probably started with a point right here, right? And then that point moved like this. So the point was going like that. Okay. So what you guys are gonna do once you take calculus is you're gonna pretend that there's a little person or this little thing, object moving in this path. You're gonna figure out how fast is it moving at a particular point. And then you also can also learn like the direction that it's moving. That's what the calculus stuff is gonna teach you. Okay. All right. Question, yeah. Oh, are the bonus one? Any ideas? Anybody kind of have an idea? All right, Kenny's got this like little thing going on. You're getting very sleepy. Basically, the length of R is the value of the radian that you rotate. So the bigger the angle of radian that you're rotating, the bigger R is going to get. Okay, yeah. The Fibonacci curve, yeah, that's might be related, but I don't think it's exactly it. Let me double check. Let me get that answer for you. Yeah, that's a good question. Why does it stop? Oh, it stops because this is good for you guys to know. Desmos only goes up to 12 theta for polar coordinates. It only inputs all the way up to 12 pi. Sorry, 12 pi. So it stopped at 12 pi. Okay. Question? Okay. Oh, there you go. Okay. They do have a slope. Yeah. So by a slope, do you mean like if there's a tangent line touching it? Well, oh, like can you represent a line using polar? Is that what you're saying? Well, you're going to learn in calc how to a derivative is like the generalization of a slope. So then yes, because you're going to learn derivatives. All right, guys. Let's see. Let me turn this off. So we're done with polar coordinates. It's a lot easier than the algebra stuff. Well, easier because that's as far as we're going to go. Here, I'll leave this here. Let's see. All right. So now I do have a warm up. Pass these out. Let's see. Give me the extra, please. Grab one, pass it down. Okay. So we're shifting gears completely. Okay, totally different stuff now. If you have extras, just hold on to them. I'll go. If you have extras, pass them to someone that needs one. If not, I'll go and collect them. Let me just write to one. All right, guys. So warm up for the first day of May. Tears of the Kingdom month. Woohoo! All right. Maybe you heard this riddle. Maybe you have not heard this riddle. Okay. So here's a little fun, famous riddle to get us started into this new section. So let's say I give you a quarter. So you start with 25 cents. I give you a quarter. You have a quarter. Oh my God, it's perfect. Today's the first of the month. Oh my God, this fucking shit lined perfectly. Sorry. Chill. Not there. That's like way more advanced than that. It's not that complicated. No. Okay. So here's the riddle. So starting today and stopping at the end of the month, see, that's why it worked out perfectly. It's like, you either, so I'm gonna give you two options. And then you have to explain why you would choose the option. The option one is I add $100 to, I give you $100 every day, pretty much. Okay, each day, boom, a bill. 100. Or every day, you double what you previously had. What you had the day before. Okay? So which option would you choose and why? So think about it, don't say it out loud. And then we'll share up. Which option do you choose? And then why? You can write this on the warm-up, or you can just answer the question. Either one's fine. I'll give you a quarter to start with. So today, it's May 1st, so a quarter. Say it again?
Will you give us whatever you choose?
The lecture today will show you which option would be better. Yeah. Oh wait, I made a typo. It's $1,000.
Oh.
Yeah.
Wait.
I made a typo, sorry.
Oh. No.
When you have an idea of which option you choose, write it down and tell me why you chose that option.
I'm sorry.
That's the reason. I mean, if you want it to be math. If you have a different reason why you chose it, that's fine too. I just kind of want to hear.
No. It's bottom, right? It's opposite.
Paper.
Yeah, like, like in the lunch. Yeah, so. And then it's. It's 31,000. How much more?
All right, let's see. I guess raise your hand if you chose option 1. Oh. Raise your hand if you chose option 2.
Okay, I'm undecided.
And then raise your hand if you're not sure. You're not sure? Okay. All right, you're not sure yet. All right, guys. So let's see what's up. So this is a good example of something growing what's called linearly and something growing exponentially. Okay. Linearly, is when something is increasing by the same amount each time. Each time you're increasing by the same constant amount. In this case, it's 1,000. Exponentially is when something is increasing by the same multiple amount. So in this case, what's the multiple that it's increasing by? Multiple of 2. Everything is being doubled each day. Okay. So let's see. Let's kind of explore this, and then we'll answer the question in a bit. Obviously, everybody seems to choose option 2. And if you did, let's see how much better off you are than option 1. And if option 1 was better, we'll see that as well. All right, let's take a look. All right, so we're gonna go back and finish this class in chapter 5. So this is section 5.1 and 5.2 about exponential function. And we're gonna also review some exponent rules that are very tricky. That might, probably haven't done in a while. Exponential function. And so I'm not gonna say what I just said. So in the real world, we'll just start off where this will be applied. Anytime a quantity increases or decreases by the same multiple amount, and it's confusing to say amount because it makes you think amount, but it's the same multiple amount. So like doubling, tripling, things like that. When this happens, what's also happening is you can say you're increasing by the same percent. When I increase something by the same percent, I'm increasing it by the same multiple amount. Okay. So anytime a quantity increases or decreases by the same multiple amount or percent, it is growing if it's increasing. And then we're going to use the word decaying if it's decreasing exponentially. A little bit of vocabulary. I'll collect the ones in the room. So a little review as the final is right around the corner. This is increasing by the same amount, right? And we're calling that linear growth. What functions did we use for that? What did they look like? Y equals mx plus b. So linear functions. So this guy's going to use linear functions. Oh, you know what? Sorry, this is not. You're writing this in your notes. Sorry about that. So from the warm up, option 1 was add $1,000 every day. This is what we're calling linear growth. And yes, you guys are right. It's going to be written as mx plus b form, linear growth. So here's the review for the final. What is the b value going to be for this particular warm-up example? It's how much you start with. B is the initial amount. And m is how much the amount you're increasing by, correct? So in this example, the function is going to be $1,000 that I'm increasing, right, every day, x plus the 25 cents. That's the linear function that models that first option. Let's take a look what the second one's going to be, knowing that it should be exponential. Option 2 was double each day. I'm just gonna say shorthand like that. But let's do a little table here. Back to tables, but thankfully X and Y's. Where here X is gonna be the day, and then Y is gonna be the amount of money. It's a little confusing that we're calling today May 1st. Okay, but today, a day hasn't passed yet, right? If I give you a quarter today, a day hasn't passed yet. So maybe you can think of this as like days past. Okay, so right now, how many days have passed? 0. So today's day 0. Just the way it would be 0 here. If I plug in 0 for X, I have 25 cents. Okay, so day 0, I have 25 cents. The next day, I doubled it. So now I have how much? Got B. Got 50 cents. Then I double that. Now I have $1. And then the next day, $2. Did I use decimals here? No. And then $4, $8, and I'll do one more. 16, and then the pattern continues, right? But here's where I want you guys to be observant of what's happening, okay? This day, what is it that you double? You double the 25 cents. So mathematically, what did you do? You do that. Added it by 2, added by itself or multiplied it by 2, right? So I'm gonna write that. This is what you did in your head. You did 0.25 times 2. Okay. This number, you multiplied it this by 2, right?
Yeah.
That means that you multiplied this by 2. Is that okay? So how many 2s have I multiplied? How many times have I, sorry, I said that back. How many times have I multiplied by 2? 2. Here I did it, I multiplied 25 cents by 2. And then here, I multiplied this by 2. So if I multiply this by 2, that's going to be 2 times 2, which I can write as 4, correct, but I'm going to write it as 2 squared instead. Okay. This, I got this because I multiplied this by 2, which means I multiplied this by 2. But 2 times 2 is 2 squared. Here. Okay. I got the 2 by multiplying the 1 by 2, right? Which means I multiplied this by 2 again. So now I got 0.25, but how many times have I multiplied by 2? 3 times. Yeah.
Wouldn't it be in the case of 0 that would work because it's 0?
Well, if I try to, you're kind of seeing a pattern, right? This is like the first power. So, and if I continue this pattern here, what do you think this should say?
1.25 times 2 to the 0.
2 to the 0. But let's see, what's 2 to the power of 0? 1.
Oh, it's 1.
Yeah. Any non-zero number to the power of 0 is going to be 1. Okay? So yes, you're noticing the pattern. Here, this would be 0.25 times 2. How many 2s have I multiplied up to here?
5, 6, sorry.
Notice that this number of 2s that I've multiplied coincides with the day. Perfect. So this is day 6. So 6 times. Okay, at the end of the month, how many days are in March? How ma- Hold on.
Why would you
I think-
keep the number?
At the end of the month is the 31st. So how many days have passed? 30 days. Right? Because today is May 1st, 0 days have passed. So by the 31st day, 30 days have passed.
Yeah.
So if I continue this pattern, after 30 days pass, I'm gonna have 0.25 to the 30th.
It's 31 days.
No, maybe it's.
But 30 days have passed. That's the confusing part. Yeah. Yeah. After 30 days, it'll be May 31st. Yeah, for 30 days. Okay. And so I think this is what you were trying to read, right, V?
260.
Damn, what is it?
260 million.
268,435,456 $456. Okay, versus here, after 30 days, plug in 30,025 cents.
At day 19, option 2 beats option 1.
Yeah, so it starts out really slow. But by the time you get to the 30th day, like it's crazy. The difference, right? All right, pass up your warm-ups. That's true, that's true. I guess I should have said, you gotta give up the money and then, but yeah.
Index.
Uh-oh, make sure your name's on them.
Just stop.
Did you guys miss your names? Some of them don't have names. Thank you for checking. So your name's on them. Oh. Misha, let me go on. One more. Couple more. Careful, careful. Okay. All right, so let's just quickly look at the graph. And then we'll go on a break. We'll continue from here. Let's take a look. All right, so look, I graphed the function that we've created. 0.25 and 2 to the power of x, depending on the number of days, right? That's the function that we were using right now. And so notice, here are the values that we were getting. It starts out really slow, but as I mentioned, by day 30th, look, I can't even freaking get day 30th. By day 30th, it was like huge. Let's put, oh my God, there we go. Yeah, it's too big, but yes, it's what you guys told me, okay? Versus if I do the linear function, it's kind of funny now.
Oh, God, flat.
It's flat, yeah. Let me go like this. There we go. Okay, so about day 15-ish, day 16, you're at about an equal amount of money. And after that, the significance is crazy different. Okay. So yes, so I just want you guys to look at the graph of an exponential function. That's what we're going to be observing in a little bit. Okay. They're going to do these these curves where they shoot up really fast. But let's go on a break. Come back at 1:57, 1:58, 1:58. We won't get there today, yeah, but we'll get there later on for sure. Yeah. Yeah. Yes. Yes. Mhm.
It's a migraine.
Yeah, I mean,
Change of weather.
it's for those reasons I record. So
I just wanted to, because I've missed a lot of classes. I was like, I really wanted to make it, but. Oh, I don't know if you get emails from
I
WeatherSign.
did.
Did you get the one?
Yeah.
But, oh, thank you
Yeah.
so much.
So,
Sorry, I mean, I have to be here. I have my bio exam on Wednesday. So I thought to be there.
Yeah.
I just, I was just in there.
so in terms of, yeah. So, we always have to
Okay.
So, like, you can have a graph like this.
It's only you're not okay with that.
So we looked at this graph, right? Yeah. Okay, but let's say you want a graph that looks like this. That below, it's a little harder for the below part, but a graph like this could be like, sounds not mean, but like population dying off, a virus. Like the population is pretty stable, and then something occurred that now that population is decreasing exponentially fast. So it'd be going this way. Versus something like this. This is also, see, this is a little different. This is assuming that, like,
It was at one point at growth, and now the growth is going.
yeah.
is,
Yeah. So if it goes like this, let's say, it could be like there was a really high amount of something, right? And then at some point, let's say it starts here, at some point, some chaotic event happened that's exponentially declining, but then it stables out. Yeah, so they're all different cases. And it depends, and that's the beauty of this one. Yeah, and there's some other more complicated ones which we don't get to cover, but they're called like logistic growth, which shoot up, but then they stable out. These are more realistic.
Oh, I've done something else.
Yeah, this is more like real, what really happens. Because something grows exponentially, but in the real world, at some point, just can't keep increasing. So there's something that stables it back up.
The one thing that's pretty much is the one that
It's like, oh, I need it.
exponential adjacent. Yeah, there's a lot of other species.
I don't know.
There must be something that carries capacity to their environment.
Yeah, like at some point, there's not enough resources anymore because the population is growing too much. When people start, or the population starts dying off.
Okay. So it's going over this. There's a way that you can distribute it maybe. Why?
Let's keep going. All right, so just real quick. Let's observe some quick facts about these graphs. What do you guys notice never happens to this graph? It's never negative. Is there an x-intercept? Let's see. So the graph goes down and you see the y values there. Let me go like really far out. Oh, ooh. Is that true? Is that true? Is that true? Is that true? Maybe I went too far out. It is not true. Okay. And that's because no matter what you plug in here, right? It's going to end up being, and we're going to go over exponent properties so you guys can see that a little bit clearer. But yes, this will always end up being a positive number. Okay. So what do you guys notice is the domain of this function? Can you plug in any negatives that you want? Can you plug in any positives? Yep, it just blows it up, right? We just can't see it, it's too high up. But yes, so the domain is all real numbers, negative infinity to infinity. What about the range? Not including 0 to infinity. Okay. So yes, as Cameron mentioned, this end behavior, right? The tail, as x goes to negative infinity, what is f of x approaching? What is y approaching? Yeah, remember, don't forget all that. That's all going to be on the final. As x approaches negative infinity, what is y approaching? 0. Okay, it looks like it's 0, but it's not. Okay. As x approaches positive infinity, what is y doing? What is y approaching? It's growing to infinity, okay? So yes, you guys are right. There is a horizontal asymptote right at y equals 0. Okay? All right, so let's see. So I just wanted to show you that. And let's write some of this stuff down, which will be helpful for your homework. Okay, so let's continue with this problem that we went on a break with. So from what we did here, from everything that we did here, this function, what was the function that we wrote down? From what we did here? 0.25 times 2 to the power of whatever x value you plug in. So you're going to write it like that. Okay? But here's what's important. This number here, kind of like the b, right? Here, this is the initial one. This is what you start with. It's the number that's not, in this case, being raised to the power of x. Okay? The x itself is the exponent. So the exponent is the input value that you plug in. And this 2 here, if this is the exponent, what is the number below it called? Starts with a B? The base. The base is always the same. That one doesn't change. As we saw here, it's always going to be a power of 2. So now, if we don't really pay attention to the application with money and everything, and we just think of it as a function, okay? What about negative x values? Here's where the exponent properties are going to start creeping in. Okay. Let's say you plugged in -1 into this function. So it's going to be 0.25 times 2 to the power of -1. Does this make this a -2? Remember, we know the range, right? It can't be negatives. So exponent property here, what do I do with this 2 to the power of -1? How can I rewrite it? Without a calculator. Whenever you have a number raised to an exponent, you write it as a reciprocal, and it's going to be 1 over 2, but now that power becomes positive. We're going to go over that, okay? So I'm going to rewrite this as the reciprocal of 1 over, but now 2 to the positive 1. So it just becomes 0.25 times 1/2. Put that in the calculator, and you get a decimal number close to 0.125. Plug in -2. You get 0.25, 2 to the power of -2. So how do I rewrite 2 to the -2? 1 over 2 to the power of +2. So it's going to be 0.25 times 1 over 2 to the power of +2. Which is just 1/4. Yeah. So 0.25 times 1/4, which is approximately going to be 0.06. But yeah, look, those values are getting hella small. And in terms of its graph, just do a little sketch so that it's in your notes. At x equals 0 is the initial amount value, right? At x equals 0 is how much you start with, which is 0.25. But x equals 0, we got 0.25. And as we saw, the graph gets close to the y-axis as x approaches negative infinity, and then it just shoots up hella fast. Like that. And so we saw a couple things. We saw that its domain is negative infinity to infinity. Its range was everything from 0, excluding 0, as you guys said, to positive infinity. And then we saw that there's a horizontal asymptote. At y equals 0. Just writing down everything we said. So that's there in your notes. And so, in general, when we're dealing with exponential functions, we're going to have it look like this in this form. Okay, the way this one turned out to look. And so we're going to use that to define an exponential function. We're going to say a function f of x equaling a times b to the power of x, where we don't want b to be 1. Why do you think we want b to be 1? What's 1 to the 3rd power?
It's one.
What's 1 to the 5th power? 1. So will the graph look something like this?
No.
No, right? It's always just going to be whatever a is, because 1 to the power of any x here is just going to be 1. So we don't want it to be 1, and you're not going to want it to be a negative. Okay, so we're going to want it to be positive. So we don't want it to be 1, and you don't want it to be negative or 0. So if you have a function of this form, so a function of that form is called an exponential function. And a is its initial amount. Or I think the textbook says initial value. How much you start with.
So it can't equal 1 and it has to be greater than 0, so it can be 0.5,
It can be 0.5,
and it can be 1.2,
and it can be 1.2.
it just can't be 1.
It just can't be 1,
Okay.
because 1.5 to the power of a number changes.
Well, yeah, because we saw it.
Yeah, exactly.
Okay.
Yeah, yeah. Exactly. So that's perfect. But yeah, let me show you some examples and let me show you some non-examples. So that way you guys can see it and be like, okay, this is exponential, this one's not. So let's say you have y equals 3 to the power of 0.5x. Here, this is example. You can also have 2 to the power of 7x. I'm just making these up, okay? And let's say the third one is 1/3 to the power of x. What's the initial value? How much do you always start with at x equals 0? 3,
2, 1.
1. Right, there's a 1 there. Okay. And so here are examples of non-exponential functions that look like they are because they use exponents, but by definition, they're not. 5x to the 7. There's an exponent, but the exponent is not the input value. Yeah. 3 negative times negative 2 to the x. Why is that one not an exponential function?
Negative.
Because the base is negative, right? It has to be positive. And then 1 to the x. That one's always just gonna be 1. That one, it's just a constant line, y equals 1. That. So as you ready to go down, let me show them to you on Desmos here. All right, here's the first one. So notice the shape, it still has that J shape. But is this a decay or a growth? It's decreasing, right? As x gets bigger, the y values are decreasing. Well, this one is, that one's increasing, so it's growth. What do you think this third one will be? Decay. So which ones are decay? Yeah, if the base, notice that if the base is lower than 1, right, then there's decay. Because the second one is saying at each day, like the one at each day, you're going to multiply what you had the previous day by 7. So that's why it's getting bigger. Or the one we did was 2, right? It's doubling. The base was bigger than 1. But what this is saying, 0.5, think of it as a half. This is saying that each day, what are you doing? You're halving it. You're losing 50% of what you had the previous day. Right? So you're being half each day, which is why it's getting smaller. This one is saying each day you're going to divide it by 3 or take a third of it each day. So it's getting smaller. Okay. When you buy a car, that price value goes down fast. Okay. So versus maybe you're a shoe collector, and the rarer the shoe, the price is going to do what? It's going to go up. So let's see decay and growth, right? You just have to determine if it's exponential or not. Okay. But yeah, so here that's why you need decay, because some examples make sense for it to be decay. Okay, and then yes, let me just show you why. Let's pick a number. Let's say 3. B to the x. And let's see if our hypothesis was right. So it can't be, it has to be greater than 0. So if my b value is greater than 1, the bigger b is, the more you're like multiplying it by, right? Doubling it, tripling it, quadrupling it. So it's going to grow hella fast. But the smaller b is, see, when it's 1, it's not interesting. But it kind of matches this pattern of the exponential functions. But once b is smaller, now you're decaying. Like that. Okay? Just to show you that. Okay. All right, let's look at the non-examples. All these 3 examples had that J curve shape. Let's look at this one. This one does not. That's a polynomial. Yeah, Jordan.
So here, let's say 5 of the water equals to 7 to the power of the place. We're going to change the. It's a big actually it's added, it's added 5 to the initial amount, so it becomes 7.
Yep. So you're just doing a vertical shift upwards 5.
Is there anything else?
You can reflect it by putting a negative out in front. Vertical reflection. But what if I put the negative, what if I put the negative in front of the x? Instead of a vertical reflection, it'll be a horizontal reflection. Now it's decaying. Why is that? Because now the negative is going to turn this into 1/7 to the x. So it's going to be smaller than 1. a negative behind the 7, the graph disappears. Because it's not an exponential.
Sure, let's make it so it doesn't spin that in the person and to- what's the line for us? Let's think of that, so it's like-
A plus or minus,
Well, the-
it'll just shift it up. It'll shift this graph 3 units up.
the same that you're starting. So, basically, you're on that and start with the-
Exactly. So it's the same y values of this graph, but all the y coordinates are going to be 3 units more than
So that's really just like.
exactly. But back to the vocabulary that we use for transformations. This is the parent, in this case, like the parent function of it. Whoops, like that. See, it shifts.
I have a related question.
Yep.
So then in the horizontal axis, there also moves.
Mhm. Good point. Yeah. So here, the original graph, right, has a horizontal asymptote at y equals 0. But now, if I shifted the entire graph 3 units up, now there's a y asymptote at y equals 3 because it shifted up as well with it. That's very important. Good observation. Cool. Okay. All right. Yeah. So look, these graphs don't show up because they're not exponential functions, and this graph is not interesting because it's just going to be 1 the whole time. All right. All right. Good. Keep going. We're getting close to the algebra part of it. Let's see. All right, so let's just write down some of the things you've noticed for these guys in general. So the first one was if the base b is greater than 1, you have growth. Right? We end up having growth. And so then all the graphs of these are going to be shooting up. Yeah. Versus if the base is less than 1, but still has to be greater than 0. So it's basically squished in between 1 and 0. Then we saw that we have good care. So in this case, the graph will shoot down. But you still have a y-intercept, y asymptote, sorry, horizontal asymptote for y equals. It's just now it's in this. So. All right. And so part of the homework, they're going to throw a function at you. And you want to be able to determine, is this an exponential function or is it not an exponential function? So you need to know how to manipulate it, bless you, to see if it turns into this form. Okay. But to do that, you're going to need to review some exponent properties. And if you took trig, you probably haven't seen these in a while. Because I don't think you guys did a lot of exponential stuff. It's a little, maybe a little bit. Let's do a review and then we're gonna play with them for a little. Okay. So there was this rule here that if you have a base to the power of some exponent n, and you multiply that to b to the m, if the two bases are the same, what did you end up doing with the exponents? You add, okay. Add them. But what if I have b to the n, and instead of multiplying it with b to the n, I just raise the entire thing to the n. You end up multiplying the exponents. Good. That. All right. Now, instead of multiplying it like I did in the first one, I end up dividing them.
We're talking about it.
You do the top exponent minus the bottom. But then the fraction's gone.
Yeah.
Huh? It becomes n minus n. These three can get a little confusing to remember to apply. Okay. I got 2 more. And then I'm gonna have you guys play with it. This one's different. This one says if I have a fraction to begin with, I just have a fraction and I raise this fraction to some exponent. Like let's say I square it. It goes to each one. And you raise the numerator to that nth power. And then you raise the denominator to the nth power as well. And then we have the negative exponent one that I just mentioned. B to the negative n, so it's going to become 1 over b to the positive n. Okay, we haven't seen them in a bit. All right, I'm going to give you guys, let's play with them, and then I'm going to have you guys test them. I'll do the first one with you. Okay, so simplify. All right, so let's say I have 5 raised to the 2 plus 3x. Does this look like this form? Right off the bat, it doesn't, right? So we need to see though. Can I write it into that form? If you can write it into that form, then that should be an exponential function. And then I might maybe know the initial value. Okay. Okay. What are the exponents doing? Adding. So which property do you think I can use? The top one, right? But you normally use it going from left to right. But you also need to know how to do it from right to left, like an identity, right? So I can rewrite this as 5 to the power of 2 times 5 to the power of 3x, which becomes, what does that become right here? 25, because that's being squared, right? And then I got 5 to the 3x. What are the 3 and the x doing? They're multiplying. The exponents are multiplying. Which property has the exponents multiply? The second one. So this one's strictly that. Okay, let me stop. So how would I be able to write 5 to the power of 3x so that I can use, if I want to go from right to left? And I want the x to be the outside one. 125. You guys see that? Okay. And by doing this, yes, then you go ahead and you say that's 5 times 5 times 5. It's 125 to the power of x. And look, boom, it's an exponential function because it's of this form. What's the initial value? 25. Does it grow fast or does it decay? It goes hella fast. It's definitely bigger than 1, and it's hella bigger than 1. Okay. All right. So what I'm going to have you guys do is I'm going to have you simplify the following expressions. Yeah, I'll go this way. Okay, let's see. So 2 to the 5x, 3x over 9. Okay, let's put the 9 there. 1 over 5 to the x. And then 3 to the negative 2x.
They all need to be simplified and like an exponential function. Or are they all not?
Yes, go for it. Simplify them as this one right here. Exponential function.
Yeah, correct.
Let me change a little bit on the notes, so this should look updated. My markers here, I'm gonna have some of you guys write your solutions on the board. Several of you are finishing up, so just check with your classmates real quick. And then I'll go around as well, but check with your classmates. And I'm gonna pick some of you guys to come write up your solution. Definitely check with your classmates.
Three students. Well, I meant to three, but you know, the views. I think that's the difference. I don't know, you know, I got the nine. I think they were consuming. What did you do that's how I got the top. They made it like one and somebody and I did the same with the X.
If it's one.
Well, I didn't get the word. My mom is like, you know, that's not clear, it's phrases, but I think it's.
Yeah.
That's fine. Yeah. Oh, cause, we did that. Well, I don't get that. Oh,
So that one, you're right.
think we're 45.
If you want to write it in this form, you don't want x to be negative.
Yeah,
So,
but it's all right. It's,
yes, that was.
oh, it's, yeah.
For this one, you don't want to x to be negative, so you do a couple of things. You use this property, it's gonna take you back, right?
Yeah.
So what you can do is you can think of, the negative as a negative one x. And then you can do kind of what we did here. You can think of the negative one and then write it as 5 to the negative 1 to the x.
I see.
You can do something like that.
So, so it's all right if I have the negative one here.
Correct.
But now it's where the.
Yeah, because if you do this, now that 5 to the negative 1, you use this rule again. And that's gonna become what?
I got you, yeah.
Yeah.
Uh-huh.
Oh, okay, let's see. What was to do from number 2? You have to do number 2. You're doing number 4. Number 2. Let's see, anybody wants to do 3, 4?
One now.
I mean, it's fine, I'm just saying, right now, I'm having to get started. So what can we do so that it looks like, and it like this, exactly. See, that exponential function. All right, take a look. Okay, let's take a look.
Yeah.
So let's see what we did here for number 2. Looks like we used property number 2. Yep, property number 2. This, and instead of writing the x inside, you write it outside. So you split it up, and then this just becomes 2 to the power of 5, which is 32. What's the initial value?
1.
1. Good, right? That's that. The a here in this case is like a 1 in front of this. All right, number 3. We got 3 to the x over 9. And then what power is 9 in terms of 3? Yeah, perfect. So this is like 3 squared. And so notice that what they did was they rewrote the 3 squared on the bottom. And they went this way. And they rewrote it as 3 to the negative 2, which they put here. Okay, timesing this 3x. By doing that, then you end up with 3. If I go backwards now, right? This just becomes 1 over 3 to the positive 2, which is where they got the 1/9. That's 3x. Okay. Another property I saw people using on this one is they use this property here as well. They subtracted the top exponent minus the bottom. That would have worked as well. All right, and I think 4 was a tricky one because that negative x. So let's see. So use property, the last property here, rewrite this as a negative exponent. But these functions don't, the general form don't have a negative x in front. So we can rewrite this as -1 times x, and then use rule number 2, which says if 2 exponents multiply, I can split it up as powers. And now what's inside, I can write it as a reciprocal. Okay. Oh, I didn't pick someone for the 5th one. Let's do that real quick. Help me out here. What can we do?
Real quick, why isn't the 4th one just 1 over 5 to the x, for like x just where the 5 is? I mean.
Because
5 negatives,
like this one,
like just right where it is in the next one. Yeah.
this one. So it's not wrong. It's just the goal of this is to try to manipulate these using these properties so that it looks like this. And in this form, x is not negative, x is positive. Yeah. Because see from here, if I asked you, is this a decay or growth? The 5 is going to throw you off. You're going to think growth. But that's because x is negative. But if you write it with a positive x, it's really, the base is 1/5. So it's really decay. That's what, okay? Here, growth or not, or decay, we're going to manipulate it, okay? So what rule can I apply here? They're multiplying. We can, since they're multiplying, let's see, maybe we try this one.
Yeah.
Okay. So I can rewrite this as 3 to the power of -2 to the positive x. So 3 to the -2,
1 over.
power of 2 to the x,
That's
1/9
to the power of.
of x. Perfect. Yep. So notice that we have decay. Okay, because the base is less than 1. And so that's kind of part of your homework. You're gonna have to do some algebra to manipulate these things. Any other questions? Yeah, Ken.
So for number 4, we can also see that the 1 is to the power, it can be to the
Oh.
power, right? And then
Here, let me do that over here. Say it again.
and then the 1 is to the power.
Any number?
Yeah, it can be, so it can, yeah. And-
Okay, sure.
Yeah, and then you use that to. Using the fourth one.
This one?
Or-
You can't do that because the exponents need to be the same.
Oh, yeah.
So you could do it.
Do that.
If you do it as x, yeah, because 1 to the power of any number will still just be 1, correct? So if you manipulate it so that you just saw this as 1 at the x, now you can go backwards and apply it this way. And then you'll get 1/5
Yeah.
to the x, which is, I think, the same answer, yeah. Yep. Yep. All right, sweet. Okay, guys, so we're gonna step away from the algebra for a little bit, go back to more function stuff. So as I showed you guys different examples, exponential functions can model different things. But when it comes to natural science or finance, there's a very famous exponential function with a very famous base. Okay. You've probably seen it, you've probably heard of it, but if not, it's okay. It's going to use an irrational number that we talked about at the beginning of the semester. So, in a lot of natural science and finance, the irrational number E, the irrational number E, that I think is approximately like 2.717 something, and so on, is used as the base of an exponential function. Okay. And so this will be the parent function, and then you can multiply it by 2 in front or all kinds of things, but this is the main parent function that is dealt with. We're going to look at, I think, next week. If you've seen this before and you don't remember where this shows up and why E shows up. Okay. Maybe the word compounding. This sounds familiar, something like that. So we'll revisit that, or if you've never heard of it, just wait till next week. We'll see where this shows up. This function is also very famous in calculus. It has memes all over the place online. You'll learn why. You get the cut. Okay. But I wanted to kind of just play with an example. Let's see, we might leave a little early. I wanted to play with an example so you guys can see how to use this and also how to do it on the calculator, because I'm going to show how to do that. And it's going to be a science example. It's going to be a biology. All right, so let's see. Sorry for making you write a word problem. So in a biology experiment, hopefully that's not too long. We're going to let n of t, just some function in terms of t, be the number of bacteria. Here we're going to look at an actual explicit example. In a colony after t hours. Slow down there. And we plug in the number of hours that have passed into this function, and then it's going to approximate the amount of bacteria. Okay. Suppose that from t equaling 4 to t equaling 8 hours, the number of bacteria is modeled. Is modeled using the function n of t equals 1.2 e to the t. So you're observing this bacteria here. And then the data shows you that from T equaling 4 to T equals 8, after you look at the data, it seems to be growing exponentially. And you plug that into the calculator, and let's say the calculator estimates some kind of modeling approximation function that looks like this. Now that you have a function to play with, now you can analyze more information about this bacteria using the skills that you learned in the pre-calculus class. Professor. Okay. So let's answer a couple questions. Lead me through them. So the first question is the bacteria growing or decaying? How do we know?
Deposit.
The base here is, since the base, B is equal to E, which if you put that in a calculator, it'll give you the decimal value, is about 2.717. It's definitely going to be bigger than 1. And therefore, we're going to have to. So the bacteria is growing, not dying. Okay. What if this was e to the negative t? Then you would do everything we just did, and it's going to become 1 over e, which with the calculator you'll see is less than 1. But for now, let's just use this. Okay. Question 2. Approximate the number of bacteria at these values that were, no, sorry, bacteria at T equals 5 and then T equals 7. So I want you guys to learn how to do that in a calculator. So go on a calculator of the one that you're going to use for your homework and figure out how to use this function to find the amount of bacteria. If you're using an iPhone, let me know. It's kind of tricky with the iPhone. So yeah, so you have to do, if you do it with the iPhone, you put the number first. And then you're gonna put it. So for example, you want to do T equals 5, you put 5. And then you first do the next one. Now it is 5. And then 10. Let's see, you're right. What you guys are doing that is right. We're gonna have 1.2 e to the 5th. 1.2 e to the 7th. Let me know if you need help with the calculator. Okay. All right. So what did we get for at T equals 5 hours? Approximately how much bacteria do we have? 178. 178. Okay. 0.1. Okay. Let's just round it to the first one here, or the whole number. We'll say bacteria. We're counting the bacteria. And then for the 7th one, for 7 hours, after 7 hours, you should have gotten something like 1,316. Okay, remember. Okay. Cool. How much bacteria? Oh, no. It's because it's from T equals 4 to T equals 8. So the question I was gonna ask you is incorrect. Okay, we're gonna end with our famous average rate of change. Okay. So now we know how much bacteria there was at 5 hours. We know how much bacteria there was at 7 hours. So I'll let you guys do this. Find the average rate of change from T equals 5 to T equals 7 hours. And interpret what that rate is telling you. Make sure your answer has units. Units. Over the change in X values or the change in. The total change in time. All right, guys, so it looks like some of you guys are forgetting. Let's see, so you're doing your average rate of change, right? What is the variable for the output in this function? Oh, crap, see, I made a mistake. N. So the function's N, number of bacteria. Okay. So in this case, it should be the change in the number of bacteria over the change in T, because in this case, it's a function of time, right? All right, so you're going to look at within this interval, the number of bacteria that you ended with, so n of 7, minus the number of bacteria that you started at 5, that you had at T equals 5, over the change in the amount of time. So you subtract the time. Okay. So when you're doing this on your homework, you're going to need to know how to do all this stuff. Okay. So that's going to be about 1316 minus 178 over 2, which I think, let me see, did you guys get 569?
Yeah.
And then what are the units? Bacteria per hour. So what is this telling you? It's growing. It's telling you on average, it's growing about 569 amount of bacteria per hour. Yeah.
No, isn't that correct with an exponential equation?
It's this average rate of change. This is why I keep doing it, because you're going to see it all in calc. It's defined for any function, regardless of the type of function you're dealing with. You can find, you can use this to interpret the data. In this case. So in this case, the exponential part was only important when you're computing the output.
In a linear function, it wouldn't matter which, like, in a linear function, if they also use hours, it would be the same from 7 to 5, from 4 to 6, from any of those, but in this, it would change depending on which hour you do it's exponential.
Exactly. Notice that, like, just within 2 hours, the amount of change was huge. And so that's kind of tracking that information. Okay, guys, that's it. That's all we have for today. Okay? You guys look beat. So take a break. If you're going to the coffee talk, they should have some pastries and some coffees. So, give you guys some energy. Good job. When we come back, we're gonna do log. Okay?
Where's the coffee cup?
In the math and engineering center.
Okay.